So, now we are going to start the third segment of the first module, and in this segment, well, if you recall, so we now have a formal understanding of terms like sample space, events, probability function and so on. So, the goal for this segment is to introduce the notion of independence, which is very fundamental in probability theory, and also the related notion of conditional probability, and work through some examples. And then we are going to look at, and we are going to do this in the context of an algorithmic problem. Okay. So, it is going to be the problem of verifying matrix multiplication. And we are going to provide a very simple randomized algorithm, and while we are doing that, we are going to leave some undefined terms, and that those terms are the ones that are going to lead to an understanding of conditional probability and independence. We will try to clarify those terms, and then finally, we will end with a well defined description of the randomized algorithm. Okay. We are going to still leave a few questions hanging at the end of this segment. For example, we will whether the algorithm is correct is going to be left out in this segment, and we will address that in a subsequent segment. So, here is the problem statement. You are given 3 n cross n matrices A, B and C, and you are asked to check if A times B equals C, and you have to output yes if they are A B equals C and no otherwise. Okay. And of course, you all will know how to solve this very easily. You just multiply A and B. Okay. There is only one downside to it. This, when you multiply, you are going to take the normal naive multiplication is going to take theta of n cubed time. Okay. And this is fine for small matrices, but nowadays the applications for matrix manipulations come from big data applications, right. Talking about very large matrices like 10,000 cross 10,000 or something like that. And so, then an n cube time algorithm becomes prohibitive. Okay. So, you need to somehow speed this up. There are some fancy algorithms that you can use. You might have heard of Strasson's algorithm, anybody. So, that brings it down to like n to the 2.89 or something like that. And then even more fancy algorithms that only theoreticians think about will bring it down to n to the 2.37. I think there has been some improvement in this n to the 2.37. I think it was 2.38 for like 20 years, and then somebody came up with a actually two people independently came up with brilliant ideas to improve it from n to the 2.38 to 2.37 or something like that. So, yeah, that is something you could do if you wanted to, but that is going to be a very complicated algorithm. But our interest is to try and do this even more efficiently and take advantage of the fact that we can design algorithms that can toss coins. Okay. Here is how this randomized algorithm is going to work. Okay. We are going to generate a column vector, and that is this vector R, and we are going to do it in a very specific way. We are going to choose, there are n bits in this column vector. Each of those bits has to be uniformly at random. So, another way of thinking about it is just flip a coin. If it is heads, make it a 1. If it is a tails, make it a 0. It has to be a fair coin. Okay. And the outcome of and we also want each of these n bits to be independent of each other. Okay. This is again a term that we have not defined well, but it just means that these coins have to be done without influencing each other. We will formally define this term shortly. Okay. And so, you will get basically R1, R2, R3, so on up to Rn. Okay. This is the column vector, and this we already have, and the same column vector shows up here as well. Okay. And here is what we are going to do. We are going to see whether A, B, R. So, matrix multiplication of A times A with B, and then matrix to vector multiplication, which gives us A, B, R, whether we are going to check if that is going to be equal to C times R. If these two are equal, we are going to output saying A B equal to C. Okay. Otherwise, if they turn out to be unequal, we are going to output saying A B is not equal to C. Okay. So, now the nice thing that you should notice immediately is that ABR can be computed in O of n squared time. Why? Because you first perform this multiplication, okay, and that is going to be an n squared multiplication. You will get a vector, and then again now you perform this multiplication. Okay. This might be reminiscent of matrix chain multiplication that you might have studied in your algorithms, right. We are exploiting the same phenomenon here as well. And so, now what we are going to get is an n squared time algorithm to compute the left hand side, and of course, we have an n squared time to compute the right hand side as well. So, this algorithm it takes only O of n squared time. Okay. Is it very clear hopefully? So, you just generate a random vector, each element chosen uniformly and independently at random, and you call that R, you compute A B R left hand side, you compute C R right hand side and check if they are equal. So, these are the terms that we will need to worry about, but here is one other pesky question that should rankle you. Why is this algorithm correct? Because we are asked to check whether A B equal to R, but what we are doing is A B R equal to C R. Okay. So, that is something we need to worry about. Okay. We will defer that question to a later sec. Now, I want to explain this notion of independence, okay. And in order to do that, there is a very nice saying. Okay. If you want to carve an elephant, how do you do that? You take a large rock and chisel away everything that does not look like an elephant, and then what you are left with is going to be an elephant. Okay. That is what we are going to do. So, if you want to try and understand independence, we are going to chisel away all notions of dependence, and what we are left with is independence. We are going to take two events A B, and we are going to see how they can depend on each other and define independence as the opposite. Okay. For that, we will need a notation, probability A given B. Okay. So, this what does this mean? It is the probability of an outcome A or an event A given a guarantee that outcome B occurred, okay, given an event B occurred. Okay. Another way to think of this is the following: you are running an experiment, okay. You repeat the and A and B are two events. You and remember what is when it's an event, you are talking about two subsets of the sample space. You basically define a new, when you say A given B, what you are doing is you are defining a new experiment. Okay. In this new experiment, you are going to take the old experiment, you are going to repeat it over and over and again until B occurs. Okay. The event B occurs, and when the event B occurs, then you check I mean whatever outcome you have, that is the outcome of this new experiment. Okay. Does that make sense? Let me repeat what I am saying. Basically, you start out with an experiment, you are concerned about two events A and B. Okay. You want to understand the probability of A given B. Okay. So, the way to think about it, at least one way to think about it, is create a new experiment in which you repeat this old experiment until B occurs. And when B occurs, whatever outcome you got in the last when B occurred is the outcome of this new experiment. Okay. And in that experiment, you want to understand the probability of A, and that is this probability of A given B. Okay. So, let us look at an example. Consider two dice that are rolled. Okay. Let us ask, I mean, so one way to exercise this understanding of this notation is we can ask what is the probability that the sum is even given that the first outcome is odd. Okay. So, let us say what you do is you roll two dice, okay, and if the first outcome is even, your condition is not satisfied. B is called the condition, right. B is not satisfied. Okay. So, that is not good enough. You keep repeating the roll, the two dice being rolled until the first die is odd. Okay. The moment the first die is odd, then you can ask, okay, is my sum even? Okay. And that is this notion of conditional probability. So, let us work that out. So, now you are going to roll 2 dice and you want to ask what is the notion of given that the first is odd. So, another way of thinking about it is you look at the sample space when 2 dice are rolled, okay. And then what you do is simply remove these outcomes, because they are not relevant to this condition. If you condition that the first die has to be an odd, only these are the relevant outcomes. Okay. So, only the ones marked green. So, now ignore all the other outcomes and just worry about these outcomes. And so, in other words, your sample space gets redefined. Okay. This is the sample space of this new experiment that I talked about. Okay. Now, you can ask what is the probability that the sum is even given that the first is odd. So, now you ignore all those outcomes that are not relevant, and then among those that are relevant marked green, you ask what are the ones that are what are the outcomes in which the sum is even, and those are marked with the smiley face. And now you can see that there are a total of 18 outcomes, equally likely outcomes marked green, out of which 9 have the smiley face. So, your probability is a half. So, now let us try to arrive at a formula for this probability of A given B. Okay. Let us first do try something. Okay. So, let us first try probability of A intersection B. Okay. This is not quite hitting the mark, because there is this other aspect to this conditional probability, right. We need to reduce the sample space somehow. Okay. So, what we are going to have to do is probability. So, basically now you have to throw away all the sample space outside of B. So, when you talk about probability of A given B, what you have to do is consider this as your sample space, and out of that you consider what is the probability that A occurred given that B occurred. Okay. So, your sample space is B, and out of that sample space what is the probability that your event of interest A occurred. Okay. And how do you achieve that? This probability of A intersection B gives you this portion, but then this is with respect to the overall sample space. So, now you have to restrict it to just B. You achieve that by in some sense normalizing over B. So, that is basically dividing by B. Okay. So, this is your formula for computing probability of A given B. And I could have just written the formula and walked away, but I would like you to think about how these formulas come about. Okay. So, now let us talk about dependence. Remember, we are going to have to we have to understand dependence to chisel it away, so that we are left with independence. So, it is easy to also think about dependence, right. If when can we say that A depends on B? If somehow when B occurs, the probability of A changes, then you know that A depends on B. The fact that B occurred somehow changed the probability of A, then you know that A is dependent on B. So, that is what we are going to write in this fashion. So, so simple. Now, we are ready to chisel it away. A does not depend on B if probability of A given B is equal to the probability of A. Nice thing is, so basically A does not depend on B. Now, we have a formula for probability of A given B, right. Just applying that formula, we get probability of A intersection A does not depend on B if and only if probability of A intersection B divided by probability of B equals probability of A. So, now will come the classic formula or definition of independence. This you might recall is the way independence is often defined. an event A is independent of B if probability of A intersection B equals to the product of the two individual probabilities, probability of A times probability of B. Okay. So, this is, you might have seen this as the very definition, but hopefully the intuition is clear as to how you are arriving at this definition. Okay. And here you should notice something. We are talking about A depending on B, but look at the condition for independence. Can you interchange A and B and still have the notion? So, there is this beauty here, there is a symmetry here. If A is independent of B, then what can you also say? B is also independent of A. So, you can actually work out the exact same notion for B, and you will get that. Okay. Thus, independence is symmetric, and B also does not depend on A if and only if A does not depend on B. So, to summarize, A and B are independent if probability of A given B equal to A, probability of B given A is equal to B, and probability of A intersection B equal to probability of A times B. Okay. All these are equivalent statements. Okay. Any questions on the notion of independence? So, now we can revisit this algorithm. So, we have to generate a column vector R of n bits chosen uniformly and independently at random. And how do we do that? Okay, we know the notion of independence. How do we actually do that? So, now what you do is for each random bit we have to do this. For I equal to 1 to n, toss a fair coin, okay, set the bit I to 1 if heads, else bit to 0, and completely forget the outcome of the toss, because the next one has to be completely independent of the previous coin toss outcomes. Okay. And you repeat this n times, you will get the vector R that you need. Now, there is an important claim here. Each of the 2 power n binary column vectors. Now, if you have a binary vector of n bits, how many outcomes, I mean, what are the total number of possible such binary vectors? There is 2 power n, right. Each of the 2 power n binary column vectors is equally likely. We want to be able to argue that each one of them is equally likely, right. So, what we know is each individual bit is equally likely to be 0 or 1. How does that imply that the entire n bit binary vector is drawn from a sample space of 2 power n n bit binary strings, each equally likely? That is the question. Okay. So, now how are we going to do it? Remember, now our sample space is 2 power n binary vectors. Okay. Pick one, any arbitrary one, you call it R1, R2 and so on up to Rn. Okay. So, vectors, I am just using the column vectors, I am using transpose over there. Remember, each bit was generated, the way you generated completely independent of each other, right. So, and if they were independent, you recall that their the probability of R1 being a certain value, R2 being a certain value and so on, those individual probabilities can be multiplied, because that is the formula for independence. We showed it for 2 events, but it extends to n events as well. Okay. So, then you take 1 by for each R1 the probability that you get the appropriate R1 is a half, appropriate R2 is a half and so on. So, you multiply half with itself n times, you get 2 raised to the minus n. So, what have we established? If you pick any one of the 2 power n binary vectors, the probability that you will get that particular binary vector is 1 by 2 raised to the n, and that is equally likely. So, now hopefully if we revisit the randomized algorithm, all the terms are clear to us. We know exactly what we mean by uniformly and independently at random, all the algorithm is clear to us. We have understood, but along the way we have understood the notion of independence of events, conditional probability. We still do not know whether it is correct. We know the running time, we know this is guaranteed to run in O of n squared time. We do not know the correctness, and we will see that in the next segment. Okay, thank you.